So thank you again for the invitation and Mr. Chairman. Good afternoon, everyone. So today I'm going to talk about fine particle recovery related to the sustainable use of natural and secondary resources. So my content of the talk will be divided into two. So starting from the general aspect in terms of sustainable development and the potential contribution for the beneficial resource utilization and its general challenges. And then the second part will be more specific to the fine particle recovery about the challenges and how we can address those challenges. So the starting off as a general picture, big picture. So one of the how to say key book published in 1972, which is called the limit to growth, which has been published by a group of people, so-called the Club of Rome. And they did the modeling of the global system, and they predicted by 2030, there is some sort of limit we will reach, and then we will have a decline of our growth. So it can be due to the food shortage, non-renewable resources, and the environmental pollution. So this book has made people aware of our global situation, and then we need to think about how to address potential issues in the future. Another important aspect is sustainable development. Nowadays, everyone knows, which has been originally proposed and defined by United Nations in another book, so-called Our Common Future. So the development should towards the minimization of North-South problem and resolving the poverty issues. Also, those developments should satisfy not only the future generations, but also in the current generation. So we need to live with in the framework of ecological limit, and it means we need to see the balance between the social, economical, and ecological goals. So in order to achieve the Sustainable Development Goals in 2015, there are two big initiatives, again, generated by United Nations. The one is called Sustainable Development Goals, and the second one is Paris Agreement, which is about the reduction of greenhouse gases. So in order to achieve those goals, a series of different initiatives has been proposed, including European Union circular economy packages. So in terms of sustainable development goals adopted in United Nations summits, which includes 17 goals, together with a series of different targets and indicators to evaluate our progress. So the main issue and then idea here is about no one will be left behind. It means everyone living in the earth has to be equally treated. So in relation to the sustainable development goals, what can be the positive contribution of beneficial resource utilization, including recycling? So if we look closely to those 17 goals, we can relatively easily find we can assist those goals by using the recycling, for example. For example, the goal 12, responsible consumption and production, which means a producer generating a consumer goods need to take care of the end-of-life product, including recycling and waste management and so on. So by by doing the recycling or sustainable resource utilization, we can assist achieving those goals. On the other hand, we can also find challenges in doing so. So I'm going to talk a little bit more about challenges specifically related to the fine particle recovery, which often carries the values. So by looking at the periodic table shown here, we can find base metal recycling is mostly above 50%, which is good. On the other hand, by looking at other elements shown in pink here, rare earth element or rare metal, often finely disseminated in high-tech products, can be relatively recycled. So what are the challenges for higher recycling rate? As I presented before, so they have a series of different technical issues associated with separation, liberation, dispersion of the different component, or the characterization. So those three main categories of technological aspects should synergistically working together to increase metal recovery or material recovery. And then those technological aspects should nicely couple with the social aspect, including education, people's awareness, and the legislation, which will enhance the waste collection. So those two aspects, social aspect and the technological aspects, should nicely coupling to address recovery, improving the recovery of the metals. So our approach, as I mentioned before, so we have the synergistic combination of the characterization, milling and dispersion of the particles, as well as selective separation. So we have collaborative work in terms of multidisciplinary and international collaborators for achieving those three key aspects. So in terms of separation and processing, we have some range of the particle we can handle. Depending on the type of separation method, we have the suitable particle size range. Here we see the different way of separating the particles. For example, we can utilize the density difference of the different components or the magnetic property difference to separate magnetic fraction from the non-magnetic fraction. Or we can utilize flotation methods using air bubbles to capture the hydrophobic material, separating from non-hydrophilic materials. So in terms of, for example, frost flotation, there is a suitable size range between 20 to 200 micron for the typical mechanical flotation cell. And depending on the particle property, we can go up to 500 micron in the case of cold flotation, who has higher hydrophobicity than many other minerals or waste materials. In terms of fine size, below 10 micron or 20 micron, which has a limitation of, which is in the limitation of mechanical flotation cell, we can apply the advanced flotation method, including two-liquid flotation method, using the oil droplet to attract the hydrophobic particle and separating from hydrophilic particle. So instead of using large air bubbles. So in terms of particle preparation, we can categorize those preparation into two. Bottom-up method, synthesizing a particle from the aqueous solution. Then we can get size, shape, homogeneous, good distribution of good size and shape particles. On the other hand, if we have natural ores or the, waste material and need to grind and making finer particles, that will end up with less size and shape controlled, more heterogeneous particle we will obtain. So this is a general case of the particle we are handling. So that will be making challenges and issues in terms of representativity and reproducibility of the characterization as well as the separation. So let's talk a little bit about representativity with this slide. So what if we have those four composite particles having a different degree of target component in dissemination and concentration? But if we measure only one particle, that will not be the representative. So we need to have the good number and mass of the particle should be characterized and as well as the separation to get the representative results. So now I'm going to talk about one of the key aspects, selective liberation dispersion. So what we want to have the ore particle waste after the milling or dispersion is this kind of situation where we have two different components fully liberated or dispersed, and then we can have the good separation afterwards. On the other hand, if we apply the conventional milling to simply apply the compression force, disregard the material boundary, we can make this kind of composite. Then we will have the negative effect on the subsequent separation process. So we would like to have selective dispersion liberation to enhance the separation performance as well as less energy consumption. So this is a case of different degree of liberation of the natural ore, increasing the degree of liberation, giving you the higher separation performance. So our work or work in general can be divided in physical or chemical methods. And then we have done some application to the wide range of materials listed here. So physical method, for example, we can apply the impact force application by use of hammer mill. Not only we can achieve the size reduction, which was not observed by the conventional rod mill compression force type milling, but also we can see the selective liberation of metallic component from non-metallic component observed by tomographic image acquisition and analysis. Also, we can apply the high electric field to disperse aggregate into primary particle size particles, also approved by the size reduction in particle size distribution. In terms of chemical methods, we can control the pH to assign the same size, same sign of the particle surface charge, and the particle will repel each other. So second aspect, selective separation. So we have been developing a series of different separation methods, as well as applying to the different materials. So including flotation and the rotation methods, which I have been briefly introduced before. So today I'm going to show you some of our previous work. This one is about coal flotation. So as you may know, we still account the coal for generating the world electricity, about 40% in a report in 2012. And then in order to feed coal into the electricity generation, we need to have the good purity coal that can be obtained through the comminution and flotation, for example. So by using the flotation method, we need to have some series of different chemicals, including so-called frother, which makes a fine and stable bubble to be attracting the hydrophobic coal particle. So one of the common frother, so-called MIBC, has a low flashing point, is around 40 degrees Celsius. So what if we use this MIBC in the summer of southern country, for example, in Australia? This region can make a high fire hazard, which actually has been reported in the past. So our idea is to have the literature review to list up the potential replacement of those frothers, as well as experimental investigation to confirm whether those listed frothers can be replacing and then having the good performance in terms of purification of the coal. So as a result, we get the comparability replacement can be possible with the two selected frothers, the Frost 250 and the pine ore, which has higher flashing point, much higher flashing point than MIBC. So another example here, we also did quite a lot of work on the gold ore flotation. As you may know, we now have the depletion of high-grade, easily extractable gold ore. And then we are expected to work on the complex refractory gold ore, which has finely disseminated gold in those ores. On the other hand, as I mentioned before, flotation has a limitation on ultrafine particle recovery, minus 10 micron, minus 20 micron. We need to have some sort of additional effort to make the selective recovery of the gold. So in this work, we have applied the steps so-called a coal oil gold agglomeration. So we are trying to capture the gold associated particle in the agglomerate of coal oil, so which is highly hydrophobic. And then we make this aggregate and then accept this aggregate with air bubbles to be lifting those aggregate to recover as a froth and concentrate. So we compare this CGA flotation as well as with the conventional flotation without CGA. And then our result is shown here in terms of gold recovery and gold grade. In almost all the size fraction we studied, the CGA flotation application is showing the higher and better results in comparison with conventional flotation methods. So in terms of gold grade, 20 to 60 times upgrade has been achieved from the head grade of 2 to 5. So we ended up highest grade is around close to the 200 gram per ton, which is quite good. Yep, the third part is about particle suspension characterization. We also did a series of work in terms of particle interaction, how particle interact to disperse or aggregate, or particle liberation dispersion analysis. So going through the suspension biology to study the macroscopic particle suspension behavior, as well as the microscopic particle-particle interactions through the zeta potential measurement and the size measurement. It can be coupled with a theoretical calculation by using DLBF theory, for example. We also did a series of different methodological development, including neutron methods, or the image analysis and the elemental mapping, which I'm going to introduce you some example today. So those characterization methods can be linked with particle behavior in concentric suspensions, which is one of my main research topic. So we can study the dispersion aggregation in terms of the fundamental particle interaction. Also, we can apply this kind of particle interaction in relation to the separation perspective in terms of flotation or to liquid flotation. So some of the example shown here, we have two examples here. And the first one is about printed circuit board particle liberation. The top three figures images showing the uncrushed PCB without crunching. So this one is optical microscope, and this one is XRF mapping results showing some concentration or distribution of the different metal component. The bottom three images showing the particles get through the hammer mill selective liberation, the size reduction, with optical microscope and XRCT and XRF mapping again. So not only getting those kind of image, we propose a new way of evaluating the particle liberation. And then we successfully getting some trend from the different liberation, the grinding conditions to evaluate the degree of liberation. And also we compare three different methods as well as complementarity and the similarity and differences amongst those three methods. Second example here is talking about characterization of the particle surface charge to evaluate particle-particle interaction within different particle systems, mimicking the pelletization of iron ore with bentonite clay binder. So we are specifically interested in the presence of gangue minerals, such as quartz or aluminum oxide. How much if we add how much or what kind of gangue mineral is affecting the interaction of the principal interaction between the hematite and the bentonite. So we can successfully extract some general trend and then finding out the effect of gangue mineral and explained by the interaction by the RWM theory. So I think I speak a bit to first anyway. So as a summary, I talked about general aspect of the sustainable development and how the resource beneficiation can be contributing to the sustainable development. And then I'll also talk about general challenges and the challenges associated with fine particle recovery, which can be addressed through the synergistic combination of those three aspects. So I'd like to thank again the organizing committee and the people helping and welcoming my talk, and the colleagues, collaborators, and the funding bodies, which is shown here at the bottom. So before I conclude my talk, I'd like to inform there are some special issues. I'm working with some journals. So if you are interested in, I'd be happy to have your interest. Yep. So thank you for your attention. I'd be happy to answer your questions if you have any.